Welcome to any combo lords joining me here today in my combo classroom mixed with some digital screen here because, as the title conveys, we're back to making some crazy graphs. One of my hobbies I like to do once in a while is to pull open a simple graphing program. I try a few here and there, but my favorite simple one is this Desmos here, and plug in some equations, not to fully mathematically analyze them, putting in mathematical terms together in different combinations to make the equation, but a little less of analyzing, at 2, what rate is the value going, or mathematical things like that we could apply. More so trying to just create some wacky, crazy shapes from a minimal amount of information. Of course, you can program something utterly complex and beautiful. In fact, if you've ever seen like a very detailed fractal animation, really that was programmed on numbers and equations, including, some equations related to colors and other things that we don't fully apply here. We can somewhat do that. We can make the lines different colors and such. And so a lot of things are just more complicated versions of this. But sort of like we were fiddling around with board games the other day and thinking, what is the simplest rules you could come up with that would still have complicated strategy? It's an interesting question to think, what is the simplest equation combos that could create the most complicated shape, or the shapes that resemble different things? Some things that we often stumble into in our graphs are, for one, things that look like optical illusions. For two, things that look like little galaxies or universes when you zoom in or out of them, or when you run them on a slider of a variable. And for three, things that look like the same patterns that natural selection led to in nature. Like, the reason our eyes happen to be this shape came from many years of evolution. Primitive proto-pre-humans did not have the exact same shape of eyes. Flowers did not look the same. Bugs did not look the same. And these things evolved over the years. And sometimes when we create a random equation, it seemingly falls into the same path that nature's evolution chose. Because we see a lot of lookalikes of eyes, bugs, flowers, things like that. And keep an eye out for, and that's something you can throw in the comments or throw in your own head, is what do these look like to you? Sort of like a Rorschach test in a way, but unlike pure ink blots that are meant to be vague, sometimes we can here even steer toward a conscious thing, like if it looks bug-like, perhaps we will edit the variable to see how bug-like we can make it. Now, somebody's mentioning a polar coordinate in the comments, and that is where we're going to do a lot of our experiments today. You see, usually when I do a graph stream like this, here's how it comes about. Once in a while, I pull open Desmos on my own to fiddle around with it, and I don't always do it that long. Sometimes 5 minutes, I'm messing around with some stuff. Other times, I go down a little rabbit hole and spend an hour fiddling around with stuff, and may find some that I find really cool. Like, for example, I threw one picture in the thumbnail of something that I was playing around with last night that made me think, my next stream should probably be graph related, because I've seen that there's a very simple twist on some things we were doing before. There are so many different combinations when we introduce a few possibilities. Like, we're going to have up to 3 thetas, and we're going to have up to 2 trig functions, and we're going to have, we allow pluses or minuses or exponentiation between those and parentheses. That leads to an insane amount of possibilities. Not to mention when you put a slider on something, because if we throw an a variable somewhere, let's see like a non-polar example to start. If I say y equals a times x, I'm adjusting a variable. If I say that now I also actually want to say it's y equals a times x to the power of b. Well, now as I twist these, they do different things, but these are just b moving with a at that spot. And these are a moving with b at that spot. And so wherever a is, b does a slightly different loop. And there's now a bigger continuum of possibilities to test. We can't just go through and see them all. When there's two variables, it's almost like impossible for me to check them all. Now, as we look further at this, we're not going to be doing much just typical linear or exponentiation-based coordinates on a typical XY graph as you're used to, where you may be more used to, we have y as what we set on one side of the equation, and this is some combination of x's and other stuff. But we're actually going to be using polar coordinates, like somebody said in the comments, r equals a times theta. And this is an example of a spiral that we can edit. Now this edit, mostly if you're far away, it sort of seems to make it grow at first. You're like, okay, I'm making the spiral grow. Although if you look closely, it's not growing just in terms of its size expanding. But, well, I guess it is, but even though it is technically growing with a multiplier on there, we can see a coil sort of unfold from there. The way that we zoom in when we multiply that, A stretches it in new ways, at least to the scale that we're looking at. Now, if we want to get wacky, we can try things like A times sine of theta, and let's set a wider range to that. And this, well, A times sine of theta actually is a quite simple one. That one's just growing the circle. But let's put the sine in there and put A theta there in the sine. And now we've gotten to the point where changing these creates radically different shapes. So if I'm at 0, we don't get anything. But when the radius is and theta is the angle essentially, so it's measuring a radial distance based on an angle. And if I set this just to 0.1, I get this shape. That's pretty wild. Now, oh no! Are you kidding? The Desmos isn't changing? I hate when it does this. I need a tech person on the team. It shows it completely on my end. If I look at... Yeah, so I have to pull open a different thing to see it. It's showing it on my end. So we've been... Hopefully the discussion part was interesting for that. A usual Domotro technical mishap. So I have to delete the thing that I'm actually seeing correctly and open a new one that this time it always works on the second time. I don't know why that's the case, but as you know, we are in the rare era where I have to do 100% of the tech for these on my own, and that leads to some silly mishaps. Here is where we were. Okay, when r equals sine of theta, we had a circle expanding. Well, no, the a's gone. Let's go back to the first thing we saw, which was a times theta. This was a circle-like spiral expanding in a twisty way. In fact, this already gives us a sort of optical illusion of sorts. If I set this really large, I set this to a particular large thing. We'll go 0 to 100, and we'll make a small step, and we'll make the animation speed go very slow and try and watch it go. This already looks like I'm trying to hypnotize you. Ooh, you are getting hypnotized by the combo classroom. But what I moved to next after that was if we throw in some trig functions, like a times sine, or we'll put the a in there, sine of a theta, all of a sudden, and we don't need this to be quite as crazy of steps anymore. We'll go from 0 to 10 now. All of a sudden, if I'm at 0, I might not see anything. But if I go up, I start to see these very crazy shapes. Now, we had to zoom in because all of this stuff in the sine turning into the radius ends up giving us the interesting trait that this maxes out at a circle based at the origin, a unit circle, meaning at the origin and radius 1. And none of the points in here go past that circle, no matter how high I set how much it's analyzing. If I tell it not to analyze very much, then it's like there, but still within the circle. If I tell it to go a little further, well, that's funny. How about even further? But here, and let's go in between. Let's say at 100 for now. It's analyzing just that much for now. As I span upward, we get all these crazy shapes. And to see the patterns a little clearer to start, let's turn the steps into only showing whole numbers. Now our steps are just on integers, and will range from, say, -20 to 20 for the integers we'll allow. So, and we'll start at 0 or 1. And if I go up, I can see there's 1. There's 2. 3. You notice anything interesting? The amount of spikes on it is always either the number if the number is odd, or twice the number if the number is even. So one amount, 2 times 2. 3, twice 4. 5, twice 6. So that's an interesting pattern we can already observe here. And when we did let the steps get intermediate, it gets quite crazy. Let's let the steps now just go on, let's see. I want to do like sixths, but it won't let me do that neatly because we're stuck in base 10. Will it let me do a fraction? Okay, yeah, cool. I didn't know they would let a fraction. That's neat. So, these are on sixths. Why did I do sixths? Because that will let me look at thirds and halves. If I just do like quarters or halves or tenths, I can't look at thirds, which is the second simplest one I'd want to look at. So now we can look at halves and thirds. So these are some halves and thirds of those, which do quite wacky shapes of their own. But this, of course, is just the start. We can do a lot of pretty insane shapes here. This is if we turn it into a secant instead of a sine. And we can also turn them into inequalities. But so far, these are all somewhat things that we have looked at in previous streams. And a little twist that I found when I was playing yesterday was often if you just add or multiply two interesting things together, you don't just get the sum of their parts, but you get something different that resembles each of their parts. And I found that if I take one simple thing like this, and we won't inequality it anymore, we'll make it a little clearer first, and I add something very simple, like even if I just add theta. This is when I took that last one, but added theta. Let's even go back to the first one, which was sine of a theta. On its own was these things. But now what if I do plus theta? Look at this weird curve. It comes out at this like really twisty bent piece of string angle, and then it sort of flattens out a bit. Now what if I go a little further? Here was the secant one too. That one was pretty wild. Now, to take it a little further, we could say add each of those. Secant of a theta plus sine of a theta. This one we need to be zoomed in a little closer to see. And this one starts giving us curvy things. When we have two trig functions, we're getting this shape with a certain amount of spikes, but they're starting to bend. Now, if I even just do this, that's almost crazier if only one of them has the A. And like I mentioned, if I give one of them B, then there's this bigger realm of possibilities to try that it's like impossible for me to test all of them, because each A changing, I'm just looking at a single B set right there, each B changing, I'm just looking at a single A set right there. And even if I put both on animation, it's based on them starting at a particular speed and location. So there's already a bigger continuum than I could even test here. There could be one that looks exactly like a smiley face or something that I don't know, because it's a very specific combination of these. But look at what shapes some of these seem to make. It's very strange. When B is -1, and A is -5, I get these 5 spines. And when you zoom in, they're not like perfectly lined up. They're like a little off. And then if I make B -1.1, it puts like webbing in the spikes. The spikes get offset, but still enclosed in this particular thing. So now let's see what happens when we change this sign right there. Minus didn't even change much compared to plus. Whoa, that's weird. Minus might have changed that. Oh yeah, we're trapped in here for now. A is sort of setting these certain like limits to where we're able to go with B. Like here we have 3, and B is sort of trapped in the 3. That's weird. Well, let's try to animate that, but really slow. Okay, that's not slow. I guess I need to make the steps really slow to make it actually go slow. Okay, that's still not slow. Okay, whatever. We won't animate it, but it looks pretty wild as you build and unbuild these. Now, going further, this is just if I take that of A of 1 and that of B of 1 and add them, and we already have quite a few varieties to test on that. And since B is already really complicated, we're going to not take a B for a moment and just look at the A's that occur under different trig combos. Because if I take the secant just with secant, I already get something interesting too. And we're going to stretch this a little wider. We're going to make it go to 1,000. Whoa. See, here we have a line. If you saw that this was the graph, you might think it's boring, but nope. There's interesting things hiding here. And look at these webs it forms sometimes. Sometimes it gets like really dense on a certain setting, like right there. If we look in here, it looks like this whole like netted web. And we can see that it's because there's a lot of like offset and stretched oval-like spikes reaching toward there. Now, let me check our chat real quick. Cool. It does look like it's fixed. That's nice. Somebody said they suggest checking the number 9. I don't know if you mean 9 for like my A setting or whatever. 9 often does weird stuff in arithmetic and such. Here, they're all going to be weird. If you meant 9 when we just had this portion, we could try that out, but it does look like there's still 9. So, not sure if 9's doing anything weird in this case, but still quite cool. Now, going forward, we're going to try and do something a little wild, which is introduce the tangent, which, warning, warning, tangent always goes pretty crazy. So, as I introduce the tangent, and let me give a little more room on this. Introducing the tangent makes it even wackier and expand all the way outward to space and beyond. Now, the other types of things we can add in here. Well, first let's fiddle around with 1 or 2 more combinations here before we expand further. It's like these strange strings unwinding. And sometimes they form shapes that are classic in math. Like these are like all these like cardioid-like shapes in cardioid-like shapes. This one's cool. Look, it's like this big loop here, and then it loops backward at the top. But that one makes a upside down version of a big loop, and then it loops backward at its top if it's upside down. Loop at the top, loop at the top, loop at the top, loop at the top. And it goes until we hit this center loop that makes it like symmetrical. And then this one just goes all the way off to the side like that. Now, if we do plus instead of minus, it just sort of flips that. And if we do times, it sort of doubles and stretches it. Now, if I remove the A, it actually makes it maybe crazier because they were following like a similar train of thought when they were a trig function analyzing A times theta each. And now they're like a little offset. They're like, one of them's analyzing right now 1/6 of theta, and one of them's analyzing theta. So it's could be even weirder when we have one of them set to... See, look at this. This is weird. It's like these two highways. And we just add this weird stretch, and then these are simple, and then, oh, we're getting complicated. Now, what really gets pretty insane looking, although it's harder to analyze what's going on in the graph, but what looks the coolest visually can be when we put a few of these on screen at a time. For example, if I say I'm going to have the secant of A theta plus sine theta be there, and I'm going to have sine of A theta plus the secant of theta. We'll flip those here, and we're going to make that one blue instead of red. And now we're going to see what it looks like when we change both of these. The red is when the secant is getting the coefficient, and the blue is when the sine is getting the coefficient. So here we get the same thing where some are simpler and loop around. Blue is sort of stuck on that little path. Blue is stuck right there. So what we'll try is giving this one a different trig function. Here's if I give that one tangent, and now it's sort of like locked within. You see, sometimes the trig functions at a certain setting, even though they do completely different things, they occasionally hit the same boundaries where they both want to not go beyond a certain limit. Now, these are spiking and spiraling around quite wildly. There's some wild ones. This one, yeah, these all are getting quite... This looks like a strange, like, alien head or something. There's sort of like one eye right there and a beak. I didn't make a second eye. Looking through these, what we're actually going to do is keep two on screen for a minute and edit what both of them are in conjunction in a careful way. What we'll try now is we're going to make them both really similar, where they're both secant and sine, but we're going to make one plus and one minus. And this might just make it symmetrical. We'll see if these maintain symmetry around that axis. They're sort of balancing each other at this state. Now, looking at if I make one multiplied and one added, now they're going to be doing quite different things. Now, let's even take away the secant, which is getting a little extra crazy, and just make them all sines. Even though I just have sines here in my equation, sines, a's, and thetas, and pluses or times, we can make elaborate shapes. Ooh, this one is an example of, we're starting to get to what I mean of some look like a bug. Doesn't this look sort of like a bug? Now, technically it's two equations, but we could phrase it like one equation. We could say we're looking at the points where either the sine of a theta plus the sine of theta equals the radius, or the sine of a theta times sine of theta equals the radius. If we stick an or between these, we could like logically phrase them as if they are one question being asked as to what points were being given. Now, although it's sort of two questions if we color it blue and red. But a little bit bug-like. Now, as we go, some of these bugs are becoming mutated. These are like all the bugs that natural selection didn't keep over history. However, this looks sort of like a dandelion flower. Not my cat dandelion, not the big fluffy dandelion who will hopefully visit later in the stream. The plant, the dandelion. So, we do get flowers, like I said, as well. These are some nice images. These are quite strange and cool. Now, let's try a similar thing where we have one set to addition and one set to multiplication, but with some other ones. This is a mild shift when we switch sine to cosine, but it does do some things at times. Let's see if that does much here. Sine and cosine are pretty often a very mild shift. So instead of that, let's try like something different, like a cosecant. So here's a cosecant is another trig function. Now, as we edit this, we have, this looks like a very digitally created highway, like you were like a project landscaper for a city designing something. And then here, ooh, this is only the coolest city landscapers design their cities like this. Now we're getting sort of webs in circular things. Now, let's see if we're able to turn any of these into inequalities or if that makes it go far too crazy. Sometimes the inequalities get too dark and blotted out. At other times, they shine cool lights. Now, let's try both. We're going to try turning them both to inequalities. This one's blocking it out at this scale, unfortunately. So the red is too dominant right there. What if we make the inequality go the other way? Nope, definitely not. Still, if we make the blue an inequality, that adds an interesting level to this, where now we're seeing places where not only is it equal, but shaded in spots where it's less than or equal. Now, ooh, some of these are just wild images. This is just like a wild image. This looks like something if you looked deep out into space while you were, you know, dreaming and meditating and on a lot of psychedelics. This is like what you'd see. Now, looking at different, it's like actually like blur. It makes your eyes weird. Like if you stare at that for a while, stare really close at it, and then look elsewhere, and it makes your vision weird for a second. So here's what I mean sometimes with the optical illusions. Some of these, as you stare at them, they sort of do strange things. There are other ones that the way in which they're an optical illusion like is by spiraling inward or outward. And to get more cool inward and outward effects, what we want to do is stick an A or a theta in front of this cosecant, especially a theta, because then even if we keep it at a single A, it'll spiral. So now when I stick a theta in front of one of these, it just goes absolutely insane. And if I stick a theta in front of that one, now let's see what it looks like when we even just zoom out. Now, this is blotting it out a little too much with that, so we have to make them equal. This is doing too much in this equation. That's doing too much. I have to limit what that one's doing. But here, if we zoom out, we're like at, here we're at just like a red and blue like screen. Now, if I zoom in, we start to see the petals. Now, what if I change the A? The A, of course, was just at, whoa, okay. Okay, here's what I mean by optical illusions. So now we're, okay, now we're all the way, oh my, whoa, okay, okay. All right, you guys ready for an optical illusion? I wish there was a button that I could push to animate scrolling in, because when I'm scrolling in, I'm like on a keypad, like carefully scrolling outward, and then I have to like jump my fingers back, because you know you can't scroll outward forever like manually. So there could be a more fluid way to zoom in on these if they had a slider. Maybe they do, I don't know, that lets you zoom in. This slider here is just to change the A, but look. So I'm zooming in. We're like, okay, we're here. We got some blue spikes. Zooming in. Okay, something's a little more interesting than blue spikes going on. All right, one more level of zoom. Whoa! Whoa! Okay, so this one's wild. Now, let's stay at this scale and change the A a bit. Whoa! Look at that. That's crazy. this right now is, two really simple, similar equations. We're literally just looking at the spots where, like, this thing plus sign is true, or the spots where this thing without plus sign is true. The front part of these equations are the same, of the blue and the red. The red just has the plus sign bit. And for anyone new, note how many spikes there are and how it lines up with whatever A value we're on. It's often the A value or twice the A value is like how many spikes there are. Like here there's sort of like 8 realms, which is twice -4. Here there's sort of like 3 spikes. Doesn't always happen when you're on a fractional value. Whoa. All right. Okay, now it's almost like a grid. At this scale, it's almost like this strange star. So, now let's change this up a tiny bit. And this was all when we had cosecant there. Let's make it only sine. This is going to be like a very simple set of equations. Blue. Oh, wait, I made blue smaller by accident. It didn't affect that last one, I don't think, but blue is sort of dominating right now. Let's make blue go behind red. Okay, now red's dominating. They're sort of in the same spot now, I guess. Oh, now they're not. Okay. See, these are such simple equations. These are the radius either being theta times sine of this slider times another theta, or that same thing plus an extra sine of theta. The second one being the reds and the first one being the blues. Look at these. Okay, sometimes we go upward, and here it looks an optical illusion in a different way. This is an optical illusion not in terms of it trips out your eyes by like making you see the wrong color or make your eye vision shaky for a minute or whatever. It's an optical illusion in that it looks sort of 3D when it isn't. If you look at this from the right angle and like blur your mind's eye a bit, this looks like a cone pointing downward and forward. You could also see it as a tunnel pointing like downward in the opposite direction of forward, like forward from you instead of forward to you. It looks like sort of either a cone pointing toward you or a tunnel pointing the other way, depending how you're looking at it. And I would call that an optical illusion, and it's crazy that you can make that just with the graph. Wow. Now, here, these are just, and that's when it's 1. That's when it's 1, the A's aren't even there. That's like if we didn't even have A's. This is what's happening, because they're multiplicative, and that was when A was 1. So here we get a lot of cool varieties on that. And instead of having one that does have plus and one that doesn't, for a variation, let's try our second one having minus the sine theta instead of having nothing. So now we have one that's plus and one that's minus. That's a different sort of back and forth. Look at how the colors go next to each other and create beautiful visual patterns together. Oh, this is interesting. So downward you got a dense realm, and outward you have a less dense realm. And look, the dense realm is contained in that strip. There's the dense realm. It has its own visual cone, its fake cone of its own sort. And there's a little extra loop. You know, if you ever are worried you're not perfect, look at this sphere, zoom in, see that little weird twig sticking out, and remember that nobody's perfect. And this one's pretty trippy. So that's just, different levels of, okay, different levels of this. And what I want to try is just, we're going to not put the minus. I liked having just a sine theta on this, but I'm going to take out the A for a minute. Sometimes we remember if we take out the A, it actually makes it more complicated if we only take it out on one, because having a multiplier change stuff on one of them but not the other will misalign them a little bit. So when they're aligned, there's going to be more spots that whichever one I put on bottom here we're seeing, it reads it like the lower of the colors goes in front to a degree. So like here red's in front, here blue's in front. Here they're not symmetrical because I changed that bit. So already this is the type of thing where if we decide to zoom, we get all these different scales of interestingness. But if we even just stay at one level and change the A, that's a whole different type of interestingness. Here's staying at a level and changing the A. So on the dense enough ones, even with one variable, it makes it too many different combos for me to analyze all of, because there's all the places I could be zoomed at and all the settings the variable could be at. Look at this. This is sort of like an upside down cone illusion with those circles and a bunch of like rays shooting out of the cone. This is wild. This is very simple. This is really just with the two equations. Now, if we wanted to get extra wild, we could even, throw on a third equation temporarily if it's too much. And this one, we're also going to set up to 1,000. And what we're going to do is make it theta times, let's say, secant of that. Is that going to get stuck on one side? Yeah, the secant's stuck on one side. So not secant, we're going to make it tangent, even though those are often wacky. So now we've added green. We'll put it in the background just in case it does too much. And green is providing a layer of what the tangent would be doing as we expand there. What about the cosecant we tried a minute ago? Is that trapped up there? All right, the green's trapped up there for now. All right, we'll change it a bit. Here's what we'll do. We'll just make this one still be sine. We're going to use only sine for a minute. How crazy can we go with just sines, A's, and thetas? Well, now I have one that adds an extra sine theta and has the A. And you know what? We got to make all four combos. We need the one that has the A missing from the first one, but in the second one. So these are my four equations. One of them is theta times sine of theta. One of them sticks an extra A in there. One of them is the one without the A plus a sine of theta. And one of them is with the one with the A plus a normal sine. And the one without the A gets the A later. Of course, there's more combos we could make. We could make them both have an A or neither have an A. But let's stay here for a moment. I think 4 colors is enough for now before I break the computer. Now, whoa, look at, whoa, that was like a weird, the purple one's doing weird, like, twisty things. Look at that, like, weird, like, bent, slightly off thing the purple's doing. No, stay there, stay there. Oh, it's really hard to make it stay somewhere. Okay, it's glitching the computer a little bit to have all this going. We're going to have to simplify it in a minute. But look at what the purple's doing right there. You see that thing? I'm trying to make it stay there. It's really hard. Okay, that. Look at what the purple's doing. It's like all bent, and then as it gets outward, it's a little less bent at each layer. Somebody had some suggestions on how to contrast these things. We will try things like that. Someone pointed out cardioids, which are a classic heart-like shape in math that has shown up in some of these, and a lot of fun different comments. Now, I do have to run and use the bathroom real quick. I gotta go pee. And while I do that, I will try and find a cool one to animate, which is going to require discarding a few extra ones and trying to find a way where we can animate this slow enough to make it work. We'll set just one of them for now. No, we'll set 2. We'll see if we can make this work. So the slowest animation speed and Our step will be really slow. Super slow. And we'll go from 0 to something. We don't need to go to 100. We'll just go to 10. Let's see. Does this work for... Oh, that's a little fast. Why is it so fast? Okay, what about just these? Okay. Can't make it go slower? 0.0001? Okay, maybe if I... Oh, step 0 to 100. That might help. Maybe won't help. Maybe if I'm really far. There's ways I've made it not go, like, insane hyperspeed before. Okay, the animator is really not liking that right now. You folks are just going to have to watch the background for a potential squirrel. I'll leave that out because sometimes they come when I stop talking. I will be back quite shortly to continue our graph stream and chat about more things. Feel free to leave any comments if you have any, and keep an eye out for if a squirrel wants to come and get that. All right, we're back. So thank you to anybody who stuck around or who joined in our little gap. Looks like the nut's still there, so no squirrel yet. But we do have a lot of fun graphs to look at. And we've just gotten to the beginning of the tip of the iceberg of all the combinations we could make of these. In fact, I would like to hear, just using this sort of equation and maybe using up to 2 of these added or subtracted from each other and ability to change the trig function or where the a's and thetas are. What's the coolest graph you can create? Because, I don't always have time to check through the comments of suggestions of graphs, but hopefully I'll find more time in the future to look at the suggestions people have left me in the past or future about which graphs they liked. But there's a lot of fun ones for us to cover here for sure. And I didn't do a formal intro, though, to any background of combo class general assembly type stuff. So real quick, let me note that I am finishing another main episode for my combo class channel where I put my sort of more fuller, professionaler, denser episodes. This next one, like I mentioned in the last stream, we'll be finally going into my take on 0 infinite nines, the number, or as we should more precisely call it, the number representation, that it's debated if it's a number, and if so, which number it represents. So, the question is more complicated than people realize, so even if you think that I'm going to be more on the side that we can say that number equals 1 and that you are also more on that side, you still might want to watch the episode because a lot of parties on both sides of the aisle are wrong about how they describe 0 infinite nines. So that episode turned out to be another longer one, which is why it's, I often put out episodes once a week on that channel, but the past few have been more 2 weeks apart and have been pretty long, 25 minutes or so of, I don't mean long stream type where my streams might be 2 hours, might be 3 hours. On the combo class channel, I make sure every minute counts. And so if it's 25 minutes, it has more content in it that I found on the topic I wanted to share than a 10-minute one. This next one may be 30 minutes. I'm still editing it down. I just finished filming the last scenes of it yesterday. I've already been editing it, but it needs a lot more editing, and it could be half an hour. So we'll see. If it is, make sure you always watch those combo class episodes, because those are where the truest, rarest content I create is, despite this being the channel with more subscribers based on the shorts, which I will be putting more of again out soon. In fact, I'm going to put one out right after the stream, even though it's a repost. I pre-uploaded it, so it's ready to go. I'll put it out after the stream, but it's a repost of one that was temporarily on the combo class channel. I temporarily had put a few shorts there. So the first few shorts of me reposting, getting into new shorts, maybe ones a few people have seen because they were on my other channel for a moment. Not that many of you have seen them, but there's a chance that the truest combo lords will have already seen the next 5 or so shorts, and then it'll be the ones nobody has seen except for me and whoever filmed it. Now, zooming into here, let's go back to not worrying about trying to make the slider of the animation work, but letting ourselves handle the slider and adding more equations to match each other. For example, here we had theta times sine of A theta times just sine of theta. Already interesting, but one of them stayed still because A isn't changing it. So we could, for example, put theta over A. What if we put a division and say that this one is multiplying by A in there, and this one's dividing by A in there? What will that cause? Well, that will certainly cause some very wacky behavior. One of them looks more line-like because it has less points going on this scale, whereas the other one looks more like flat bars with arrows in them almost, because that's where so many lines of their equation overlap. When you have
an infinite amount of lines in certain points, and lines are actually infinitely thin, yet we must display them to the human eye. Desmos can only do so much. They have to make certain choices of how wide do I display the lines so that it's visible to the human eye, but, you know, tries to make it clear that when this is happening, these are a bunch of lines, not a filled-in section, and that really there are gaps everywhere in here, but that the gaps aren't showing here because if we showed the gaps, we would only see a white screen because lines are infinitely thin. Now, divided by A did make a much simpler thing out there. So what I'm going to try is putting times A on the outside of this one. So now it has a times A on the outside and a divided by A within the sign. Well, okay. This is actually going so slow that what I'm going to do is just restart Desmos. That helps sometimes. So I'm going to, if I restart Desmos and just plug these back in, that genuinely sometimes helps in terms of the speed of, like, it was thinking too hard on that page or something. So here what we're going to do is we're going to make one that's A times theta times sine of A over theta. So that one has like an A times on the outside and then divides it out there sort of. And this one right here, and we'll make it go quite analyze a lot. Although right here we see, ooh, it's not seeming to do much. But as I grow it, it will form this universe that expands in and out. All right, now we're going to make one that has what looks like A's canceling out here. Like, oh no, wait. The thetas are what look like cancel out there. Let's switch this. Let's make this one theta over A, which was actually what I had meant to do. But now we have two different options. These two spiral together in an interest. Blue comes out first, and then we see red popping out. Now that's also just if we are changing the A. The zooming changes a whole different scale when we go in or out. Now, here what I had originally meant to do was this blue one, and to have this one not have the A and just go A times theta in there like we had before, or even just times theta, like as if these A's cancel out. But that's gonna not change, I guess. So we want an A somewhere in there. So this blue one's much smaller, but it's sort of at the center there. The blue one does... Ooh, that was interesting. Here, look. They formed this interesting symmetry. Cone on anti-cone. Then as we go in, and we edit it a bit, we get a lot of different formations. Oh, this might be smaller because it's analyzing less room. Let's make it analyze as much room. Now it's bigger. Now that it's analyzing a lot more. Maybe they're analyzing too much, though. Let's cut a digit off of how much they're each analyzing. Now it's a little... Ooh, cone on cone. Now it's a little clearer to see. But they're not going quite as far as they used to be. Let's put them back to 1,000. And in fact, here's what we'll try. We'll try negative 500 to 500. We'll go from the negative end included 2, adds its own type of symmetry. Now this is blotting out too much of the screen. So we got to go back a little simpler. The ones that started out quite crazy are, even if we just have theta times sine of A theta. This was one of the ones that, as you zoom on different scale, well, maybe the negative 500 was not helping. As we zoom on different scales, we can see these spirals. You might not be able to see them very well here because it's doing a lot. Wow, look, this one simple equation forms these crazy petals as you go in. It's like hard to see that they're petals. You're like, okay, these are boring lines. Okay, now they have these little loops. Okay, the loops are like shading on them almost. Now, the ones that were really expanding in a strange way as we zoom out were maybe ones that... Let's try this. If I put a theta in there. No, that's just going to make the theta squared. So... I'm not sure why it's blotting out so much of the screen. It must be the scale I'm at or how much I'm allowing in. Maybe I need to allow less in and go back to like 100. So, here's a little flower thing. Wow, that already looks like spinning. Look, as you go on it, doesn't it look like it rotates? This is one of those optical illusions. It looks like it like spins to the right, the shape that's there. Doesn't it kind of? Because as you see more of it, it like reveals the right part. So here, let's first just go to a few variations on here that don't fix it in the middle, like a secant. As we zoom in or out, we see different scales of wildness. And what happens if I make that one full? So this is if it's a little more full even. Now, what we had before was adding or subtracting different combinations of these. And what were some of the variations that I had tried on my own? Something that I hope doesn't break it is if I try and put an exponent there, the graph doesn't always like this, but it can be pretty wild when we put an exponent somewhere in there. So look at this weirder one. This one's like fuzzy on certain points because it has like a little bit of back and forth right there. This looks like when they're trying to send the signal of the other one, there's some static got on the radio or something. Whoa, this like spirals outward a bit. Spiral, and then it like forms these 3 spikes. But at 2, it's doing that. That's trippy. Look, 3 is doing this, but 2 is doing this. This lower rate. Whoa, and there's 1. This is 1.1. Whoa. Now, if that works, we're going to try and copy that into a different color to make a variation. And what we'll start with is, even if we just change one little thing like that, that seems like it would make it more boring. It can sometimes make it go wild. In that case, it's sort of left it on one side or another, and it's doing a little too much of a flip-floppy thing. Let's even take the A's out of both of them. That's interesting. Now they're on different sides. They're forming this strange equilibrium sometimes. Now, this, we're going to switch a bit, and we're going to try and put A to the theta. I'm not sure if it's going to like that a lot less. A to the theta might bug it out a little bit. Oh no, don't zoom in on the page, zoom in on the graph. So, what's going on here? Zoom in on the graph. No, not on the page. Okay, it's having trouble doing this. These equations are really tripping it up. Let's put just blue for a minute. Okay, it's still having too much trouble on this. We need to remove part of these equations. We need to simplify this a bit. What? Why add slider for T? Okay, it's tripping out. It wants a slider for T because T was the first letter in theta. And now it's... Okay, we got to restart the Desmos again, I guess. I got to be careful with when I do really crazy equations on it. When you put the exponents, it freaks it out sometimes. I don't know what's happening. Restart your page. Okay, look at the chat while I'm restarting this. Thank you all for joining me. Lots of good, cool comments. And I appreciate all of you. You're all super awesome. And looking at more variations here, the ones we started at were this. And then if we add or subtract a different type of trig function with or without certain things in it, it gets wacky. And here's a new one. This forms a little corridor. It's like empty in between these two bendy things. The corridor is in between when y is 0 and when y is 1 it approaches. So is it y equals 1? Yeah. Looks like it approaches y equals 1 there. And then if we take this and we flip it in some way, now we get an interesting symmetry of sorts. Oh, okay, maybe not symmetry. Maybe wackiness a tree. Oh, what's that? All right. Now, ooh, those are cool. Whoa, this is interesting. This one like splits in half a bit. It has a little green bit down it. Right there. Now, I don't know if it's sacrilegious, but what if we try taking one of these and seeing if it lines up in any way with signs of a different type of equation that we involve x's in. Like, if I take x times sine of ax for y and compare it to theta times sine of a theta for r, do these ever line up or bear any resemblance? It might be coincidental because they probably won't, because theta is being judged on a different scale, like, you know, you measure angles in radians or degrees or such, as opposed to here we are measuring coordinates in a different way. But it still is pretty fun. The green isn't changing as much here. But we could, if we want to give it a friend, put one of our extra special old ones, like sine equals x squared plus sine, or sine of x squared plus sine of y squared equaling a. Now, these aren't going to line up necessarily, but they are going to form an interesting friendship. But sometimes we may have to stick more so to one or the other if we want to see spots where they actually line up with other similar equations. Like if I was in this zone and I made one of them tangent, we might see them line up with the others in certain ways. Now, back to the radius ones for a bit. Here, we're going to create just some ones that are just different colors of the different trig functions on the same scale using a very simple thing, but one for each of a bunch of different trig functions. So here's a cotangent for a tangent, a cosecant for a secant. We'll do a sine and a cosine. Let's see. Sine, tan, cotan. Oh, we're missing secant. If we include that, secant and cosecant. Of course, there are other ones we could include, but these are some of our main ones. And now, we do have a lot going on here. I'm going to set them all to 1,000 to start, even though it might blot some stuff off on certain scales. And we're going to go through some different A's and some different scales. But, you know, since they're so crazy, we're going to actually chop a 0 off how much it's analyzing of each one. So, here, we can't see much because there's so many going on. But if we zoom in, we can see what's actually going different on these. As we start really, really close, it looks like nothing. We're like zooming into a little point. As you go out, you see some of them curve a little bit. Oh, blue takes a weird trip there. Green takes a little loop right there. black meets blue where it took its trip and doesn't seem to touch the center. And as we zoom out, these strange tangles become petals of a strange like flower thing. So here we got our strange flower thing. You zoom in. Here it's clear. Here it's trippy. Here it's chaotic and hard to tell what's going on. And then we're back to almost overly simple. Little lines coming out like regular and a few taking little obvious detours. Now, this is just the start of where we can go from here, because what we're going to put on each of these is adding one of these things without. We're going to add this, but for each one. This is the stream. I might be done with the stream relatively soon because I want to work on some editing and I need to cook some good dinner. But we are going to see if this breaks the computer. Hopefully not, because I don't want to end right away. Which I'm going to try and put all of them matching something we had tried earlier. Themself, but plus themself minus the A. Okay. So here we're at this scale. And let's see what happens as we zoom out. Well, some things are bouncing around. Some things are forming paths. Oh. Now, if I were to set these to 1,000 instead, it's going to make them pretty dense. But let's see what happens. It might be blotting them all out, and we might even want to change the order we're seeing them in, because whichever one I put on the bottom takes sort of priority over whichever one I put on the top. Also, these are both red. I need another color. We'll make that one orange. But here it just looks like everything's blotted out. And if I click on one, I can see where it is more. Like, there's the blacks. There's the reds. There's the oranges. And you get blues, greens, and purples. But then they're sort of given this priority there. Like if I drag green down, we might see green on top to a degree. But what happens if we zoom in a bit? Because they're not inequalities. They're not actually blotting out this portion of the screen. No, don't zoom in on the page. Zoom in on the thing. Sometimes I think that when it has trouble zooming on the page, it just quits and tells the computer, I'm not zooming in on like the app or whatever, the interface. It's like, I'm not doing this. You just zoom in on yourself, computer. And then it's like, no, I don't want to zoom in just on the screen. I want to actually use the website's zoom. So yeah, like this isn't what I don't want. Okay, there. This does look cool. Look at these orange spines forming. These orange things showing up. So like, let's put orange a little lower to see those a little better. Well, now orange is too low, but see, there's if orange is there with blue showing between it. And there's if blue with orange showing. That's interesting. Look at the blue-orange. And now I'm going to put blue behind orange. There's blue-orange the different way. They each like show each other in this rippled way, depending which is on top. Now, zooming in further. No, okay, I'll click this button to zoom. That can't go wrong, can it? So I click, it goes divide by 0 error, and then the stream crashes. So now we're starting to see certain details of why these things look their ways, but it's looking denser than when we were at the outward scale. So now let's zoom in a little more. And as we zoom in more, which it's just doing in a jumpy way right now, we start to see more and more details of different ones. Right now, the orange is starting to become clear. The green still isn't that clear. If we zoom in on a certain scale, I imagine the green will become clear, as opposed to like a big old path. Now, I'm trying to zoom in. It's the computer's having a hard time on this. Let's get rid of 1 or 2. We're going to get rid of the tangents. Tangent and cotangent we're going to get rid of. Even though the way they name these are really weird. Cotangent to tangent is not like a matching relationship for cosine to sine or cosecant to secant. They name them in a kind of wrong way. That's probably going to be an episode in like 2 years or something. Is going to be like why the trig functions are named wrong. But we already have another why the so-and-so is done wrong coming soon after my Point Infinite Nines episode, which will be out in a day or two on the Convo class channel. The one after that is going to be an episode I've already begun filming that's about why times tables are taught wrong. A subject I've mentioned in some bonus footage and stuff, but that we need to get to fully the bottom of. Also, to anybody who likes my Convo class episodes, I made playlists of grade -1 and of grade -2 so far in order on the Combo Class channel. So if you ever want to catch up on the episodes, you could watch them in a playlist, and then if you're bored and you don't know what to click next, it'll go to the next episode in order. So check out those playlists sometime. We have grade -1 and almost half of grade -2 because the next episode might be the last episode before we are halfway, like into grade -2. So when October hits, or sometime either at the beginning or early October, we'll probably be at the halfway point of grade -2. And we have a lot of good stuff that I've planned for the second half of this grade. Now, even with just 4 equations here, it looks rather dense and crazy. Let's zoom back out now that we are down to just 4. Here's what I'll try another time. I should download, I think they might have a Desmos app I could download somehow. That'll probably not have the glitchiness that the computer is doing here and does occasionally. Still, quite cool. As we click out, we're getting different scales. You see here, too dark. Everything is blotted out. But if we zoom in just 1 layer, look at all that detail that we can see. And as you zoom in, you can like see more clarity on what was actually happening in those giant curves. Now, what we're going to do is instead of having so many different things here, we're just going to take sine and secant, but we're going to copy them and we're going to make them each have a clone that's these things multiplied together without the extra theta. So, now we have these things. We need to make them have as big of a range, too. Oh, whoa! I was going to say that's too much, but it looks really cool. That's wild. Alright, let's peer into the void. See what's going on inside the void real quick. So there's inside the void. And as you go out, see, inside the void isn't always as scary as peering at the void from afar. But also maybe not as beautiful. So here we are peering at the void from afar. Scary but beautiful. Now, if we just change these a little bit, we're going to get some more wacky stuff because I almost forgot because I didn't want to mess with any of the levers while the computer was having trouble. But this is just when A is -5. We can change what A is. So, look at these crazy patterns. This is just wild. Now, I'm going to go to this one for a moment. It's hard to make it stay on one. Yeah, I need to make this bigger for a moment so I can, like, get it to a particular one. Yeah, I want it on that one. Now, let's zoom in here and see how the black background is not pure black. If we zoom in, we'll see what's going on with the black background. Well, the black background is taking a while to expose its glory. It's also just having trouble zooming. As we go in super far. Okay, the black background, I guess, forms lines or line-like things at that point. But it's really hard to tell. We're going to zoom back a bit, and we're going to make the black one go a little less crazy. How could we do that? We could do that by removing the theta from the outside, so it's multiplying by a little less stuff. However, that makes it just form a small ball that it'll be changing within. That's okay. Let's see what's happening there. Oh, also one thing that went wrong is this one is a copy of this. Well, also it's the same color, but also it's a copy of that one as opposed to adding the multiplying thing I wanted. But now the black one is just forming this one like ball-like thing that's these two webs touching. It's two like webbed ball thing. Oh, they look like eyeballs now. Whoa, it's like two eyeballs looking at each other. Doesn't that look like two eyes staring at each other? Now, can I put the theta back? Will it accept that here? Or is that just going to be doing too much? I don't know if it likes that. We're going to put minus instead. Why is the black one so much crazier? Is that just because it's at the bottom? Yeah, whichever one's at the bottom is sort of dominating a little bit. So there's a little too much power with what's going on here. Maybe we'll first try reducing how much it's analyzing down by cutting off a digit of how much the theta is being interpreted as. And now we can see the black one does simplify a bit. Whoa. The green one's still going extra crazy because that one's multiplied still. Okay. Now, if we zoom in here, we see like this dusky vapor. Here it's like you're going from afar and you see like this little blob. And then you're like, whoa, there's some weird vapor in the air that seems to be forming spirals. And you're like, oh no, they're real spirals. All right. Whoa. No, whoa. That like built and unbuilt it real quick. Whoa. All right. Now what we're going to try is we're just going to make 3. And we're going to go back to having them each be a different trig function. But what we're going to add is we are going to let them... Now, here's what we're going to do. We're just going to do the mixes of sines and secants, but we're going to add a b. Now, we've tried similar things here before. But we're going to see if it's too much to... We'll use this as our jumping off point again, because we've seen similar experiments from here that worked quite well. And here, as we build it and go outward, we're already seeing like, well, those lines look crazy. But the thing is, they just look like lines right here. We don't see that they have cool spiral shapes till about here. Then you're like, okay, these things aren't just lines. They have cool spiral shapes. All right. Also taking a quick peek at our chat. Thank you all for joining and commenting. I love you all so much. Now, let's now just see what happens when we change A versus B. Now, we'll go to a scale of like 50 away or something. So, here will be our scale. Now, if I change B, this changes. If I change A, these change. We're a little too close, maybe, to see these full patterns. Here is the things. This is like getting to the type of thing I had in my thumbnail, where look at, it looks like an inequality I designed just because some parts are filled in, but other parts have these webbings. So it's like these weird rays shooting out from the middle of a place, creating these webs. And like I said in the title, we're creating almost, well, at least the temporary title I started the stream as is that we're creating whole universes out of these graphs. And it is in a way, because it looks like a whole like big bang of a universe and different things coming out. And if we want to see what's next in the universe, we could imagine one version of that being sliding the A or sliding the B. We could also imagine a different form of next in the universe being if we added to how much theta it is analyzing. Like, where was a scale where I could actually see this better? For example, if I'm like here, let's see. It's hard to find a combo of them where they look clear enough. What if I set B to 0? Okay, there. B is 0 right now, though. So, now, this, if I, well, yeah, so if B is 0, and that's working so cool right there, we might want to simplify this, because B being 0 makes this really simple. It's theta times sine of 0. But in any case, this graph, it's like, if we want to imagine this as a universe expanding, we could say, like, what happens when I, like, add a 0 to these? Although it would actually be going slower. It'd be like if you slowly expand these. And our universe is growing, even though it's currently just trapped in those folds. It looked kind of cooler when we just had them at 100, though, so we're going to go back to that because it was having a little trouble viewing all of 1000. Now, where's the other colors? It's hard to even see the blue and stuff. I guess because green's at the bottom. A lot of options for what we put at the bottom. Anyway, that's when B is 0. And there are other things we could try. I wonder if they allow. There's a weird experiment that just popped in my head. Do they allow mods in polar coordinates? Yeah. So this is saying plus A in mod 1. So if we can add mods, let me try something weird. What if we try this thing in mod A? Now, this relates to modular arithmetic that we've done on the channels, although it's a more like continuous modular thing where we're allowing fractions and stuff. Modular arithmetic often is used in number theory with whole numbers, but here, even using continuous ranges, we could try and look at essentially the remainder is being displayed that this result would have if divided by A. Okay, so this is not going very far. This is completely blotted out currently, and it's making it go really slow too. So I don't know if the mods are going to work for that part. It's making it go really slow and crazy. We'll try, I'll figure out on my own time how to combine the mods with that. Anyway, we can remove that for now and try other experiments for sure. What we can try here is, for example, saying, what if we divide by, well, theta, that would just cancel out. So what if we divide by, say, sine of theta? So here's if I take one of those simpler ones I had before, but then divide by another even simpler one. Well, as I change it, we do get, like, sometimes they're more linear on this one. And sometimes they get all curvy and wild. That one's pretty cool. Ooh, that one's interesting. And we're going to try a similar version for these ones. So this one, we said secant over sine was the first one. Well, let's try secant over secant. Whoa, why is that? I was in caps, so it doesn't like all caps. And then we're going to try sine over sine. And we're going to try Sign over secant is the other one. So, now these form their own unique little shapes. That one made these two things, that one made that circle, these ones made whole rays. So these are doing entirely different things right now. But let's see. Whoa! Okay, so they do change in a crazy way. This is when they're each set to 2. When they're each set to 1. That looks pretty. So there's when they're set to 1. Here's if we go a little further in different ways. When we get to 2, it likes when it's a whole number for sure. Let's check out the whole numbers. This is when we're at 3. That's pretty neat. How about 4? 4. Trippy. How about 5? 5. Pretty neat. Okay, now, what we're going to try, this might be dangerous, but we're going to put a B in the bottoms of these. Now, we might have to zoom in to see, where'd the other ones go? The other ones vanished on the, because B is 0. So this now, we might need to set them both to whole numbers to make it, okay. What we're going to try is I'm going to, since this function's a lot easier on whole numbers, I'm going to make the step so it's only doing whole numbers. We'll get whole numbers between, we'll do 0 and 20 with a step of 1. Yeah. So now it's only going on whole numbers. So when B is 0, this is what our different, oh no, my Mac's low on power. Okay, let me make sure this gets set up. Okay, let me get this plugged in. This is going to be possibly a brief intermission amount of time while I get the computer plugged into the wall with the extension cord. So enjoy a cool image for now. Leave comments about your favorite types of graph or shape or thing in the universe. I'm going to plug this in so to make sure that we don't die. 10%. Okay, I have time. Okay. It will, within 3 or so minutes, I will have this plugged into the wall properly, but I need to get the extension cord. So, yeah, the extension cord's inside, but I'll be back soon.
Okay. Alright, gotta get this plugged in, and then computer won't die. And then we can have a casual bit of more graphs and not have to rush our outro. It is going to start charging in a second, hopefully. I need an extension cord to make it work, and that's why I should come prepared with all my tools and cords. Is that the clickedness that has it charging? We charging? No. Are we charging? Yeah. Yes, charge it. Okay. Success. Now, thank you to anyone who stuck around and waited and hung out, staring at this interesting graph that, if you're new, this graph isn't even the full interestingness, because you gotta zoom at different levels to see how cool the graph is. And even more so, you gotta change the A's and the B's. So, what I've done is I've thrown a B in the denominator of these 4 similar functions. Each of them have just secant or sine in a different combination on the top or bottom, and then the same rest of it. And let's change these A's and B's a bit and see what happens. So when B is set to 0, A makes these shapes where some of them, we're only seeing blues and reds when B is set to 0. When B is set to 1, we get all the colors. Somebody asked in the chat, checking our chat while I mess with this, somebody asked, my favorite thing in the universe, or maybe Stick said it's his favorite, is the universe in the set of things that are in the universe. Yeah, it's an interesting question. Sometimes set theory breaks for similar reasons when you wonder if the set is included of the things like, even not the set of all sets, but like the set of things that aren't in sets, and things like that can break it. There are actual specific paradoxes that reminds me of, such as Gödel's incompleteness theorem and Russell's paradoxes and such. And I will be making episodes about them because my favorite author, Raymond Smullyan, wrote about those a bit and has some cool, like, philosophical analogies about those that led me to understand them better. Here we have like a grid-like effect, and then as you go up, it's like, nope, our grid has changed. So these are all when B is 1. What about when B is 2? These are our options when B is 2. This is wild. Okay. Now, so the other chat comment that I was going to answer, somebody asked, is the universe a subset of the multiverse? In terms of what the terms are used for, yes. In terms of what we know about our universe in actual physics, we don't know. It's unknown, as scientists are concerned, whether there is anything outside the bubble of the universe. To a degree, we are like a rat in the cage of its experiment, trying to analyze outside the glass walls of its tank. And it's a little hard, maybe the rat can analyze its environment perfectly, but it might be hard for it to get info about outside of its experiment. Or even if it could get outside of its glass tank, outside the room it's in or something. Now, I've read interesting things about ways in which we could try and detect if there is something outside the universe. For example, there are certain maybe gravitational or similar effects that if we observed them, they could imply something that was coming not from within, but something that was being pushed upon from outward in some way. Also, we could imagine ways in which, if our universe is expanding,
there could be implications to try and test somehow of if it's expanding into any surface. Now, that is unknown and one of the great mysteries of the universe, whether there's other universes or not. The, top scientists would not claim to know for sure. Many of them would guess, possibly, that our universe could be the only one, but others would guess the other way as well. And none would say we know for sure. Now, as far as science fiction, or if we use the terms, is concerned, universe semantically usually is used to mean subset of, or multiverse is usually used semantically to mean something that is beyond the universe and contains other similar universe-esque things. Now, let's change these a bit more. Trust me, we'll investigate the universe and philosophy as we go on. I have a lot to say about that, but we got a little more math to cover first. A few more squirrels to feed. For those who liked the squirrels, you're not going to have to wait for my whole episode that I'm making about squirrels that I'm slowly collecting footage for that you'll highly enjoy, but well, this is interesting. When they're both 4, it's that. What about if they're both 5? Look, when they're both the same number. It balances out. 5, 6, 6. 7, 7. And when this one's 1 more than that, it makes this spider-like thing. When that one's 1 more, it makes an inverse spider, and they have different relationships. Now, I was saying, for those who like the squirrel feeding chronicles of how me and one of my other neighbors have been taming these wild neighborhood squirrels that we're just eating from the fruit trees and random things like that. And we decided, after the neighbor already was doing it, I decided it was okay to start giving them nuts. And now they come to me for nuts, and they're some of the combo class budget does now go toward walnuts for squirrels, but they're very cheap. I'm just very, I don't have much budget, so I don't spend it on many things. But despite these being cheap, they are included now in the combo class budget is walnuts for the squirrels. And for those who enjoy that, you're not going to have to wait for the whole episode I'm crafting about that, because there's also several squirrel cameos in the next episode about Point Infinite Nines. I will see if I can get that episode out tomorrow, but it's half an hour. And there's a bit where I'm not sure if or what I will include from this, but I called my uncle, who highly doubts that 0.infinite9s could ever equal 1 on Zoom. And I warned him in advance that I'd be filming it and I might use it in my episode, so he's aware of that. And so I'm going to see if I might use some of the Zoom call of me trying to convince my uncle that stuff that you'll hear in the episode. But the thing is, I'm not sure what I can include from that, because I did half convince him. I convinced him of a few points that were really important, but he was a doubter of certain very simple fundamental mathematic things. And so I realized at one point, it started becoming a different sort of mathematical debate, where at one point he said that he thought I said, if we don't allow infinite decimals, how are we going to describe pi? Because it doesn't have a fraction of whole numbers. And just as a jumping off point. And he said that he thought pi wasn't a number. And then I asked, really? And he's like, yeah, I think it might not be a number. It might just be approximating something. And as interesting as it is to think about that pi's irrationality and transcendental nature make it different, if somebody believes that an irrational number is not a number because it's irrational, he didn't care about the transcendental part. He felt the same way about square root of 2. It was the irrational nature. it felt sort of like at one point I was like, I'm not really going to be able to convince you anything meaningful about whether point infinite nines equals 0 in equals 1 in any circumstances if we're having this debate of a like whole previous or like a separate level about whether an irrational number exists or not. It's like, interesting debate, but if we're talking math, we have to allow pi to be called a number like all mathematicians would say. Now, so despite that, I semi-convinced him some things, so we'll see if I include any of that. And somebody left a demonstration in the comments using 1/3. That is an excellent demonstration, and in fact one that I used briefly in the episode. But let's note, I am also coming not just against the people who say that 0 point infinite nines can't equal 1 ever. They are the main targets of needing to be taught new things in this episode. But there's another target. The people who think that it must equal 1, and that, for example, not that the commenter said this. I don't, have any reason to believe the commenter is among this group. This is, a cool combo lord who comments a bunch. But in general, this demonstration they left, some people describe it as a proof. And we have to be careful because that is not quite a proof. Once again, not that the commenter said it was. It's a great demonstration, and in fact, one I left in the episode. But some people say that that proves that it is equal to 1. And before I start the episode, I want you to think about, is that a proof? I mean, before the episode drops in a day or two, I want all of you to think about who are comfortable with that 1/3 proof. What assumptions is that making? A proof doesn't make any assumptions. It has to state which axioms are its assumptions. Can't leave those unstated. But there's other assumptions that this proof is making. One, for example, is that it's assuming that 0 point infinite threes exists. So we almost have to start at an earlier level if we really want to conclusively prove this to people and be like, do these numbers, or are these numbers? Do these digit strings represent numbers? So we're going to include that demonstration, and we're also going to include how some people overstate it. And the reason I mention that is just because even people who think they know point infinite nines equals 1, that's not the whole point of my episode. The end point is closer to that it equals 1 than that it doesn't. That doesn't really spoil anything. You folks probably know I think that, but it's a lot more nuanced than that. And the nuance made in an episode that will probably be half an hour. I'm still editing it, but I'm sitting at it's edited down to over half an hour, and I have to see what I can cut. So we'll see how long the episode is, but that'll be out in a day or two. Will be a super fun one. I am going to wrap up our stream pretty soon because while these are super fun combinations of graphs, I not only want to do more editing on that episode, I want to cook a nice dinner because I went shopping before the stream and I haven't eaten any of the food I shopped for yet. And I did buy not only a bunch of vegetables, but also, and fruits. I also bought, sorry vegetarians, I was a vegetarian for 5 years, maybe 5 or 6 years back in the day. And I understand, but sorry vegetarians, but I bought a discount steak and I'm going to cook up a very nice steak after this stream because there's a steak that was on sale that I was like, oh, that looks good. And you folks don't even know, but we'll do a cooking tutorial someday. I can cook a really good steak. Let me show you. Do you have a picture of one of the ones I've cooked before? Now, let me see if it can recognize if I search steak on the, yeah. So, all I'm saying, folks, is I can cook a good steak. So, there's a picture of one I made the other day before. I'm going to be making another real good steak Let's see, that's a close-up of that one. We're going to be making another real nice steak tonight. But, however, we're also going to cook a lot of vegetables and other things. You need a balanced diet. I also bought some fruits that I brought a few of out here that are a continuation of our Pluot Chronicles. And before I wrap up the stream, I need to show you the continuation of the Pluot Chronicles. I'll keep scrolling through the graphs because some people like those. And I'm included in that, some people. But, so we've been looking at the Pluot Plumcott conspiracy as a few levels. One is that I don't think all the things in the store that they call Pluots are technically using the term right, because when I looked it up, Pluot was a trademarked term for a specific breed, and that the generic term is called a Plumcott. Similar, an Aprium is a generic term for a trademark breed, and an Apri Plum is the generic term and not the trademark one. And so, and the difference of those in general are Pluot / Plumcott, or a combo of plum and apricot that has more plum than apricot in it. An Aprium / Apriplum are just the opposite, a combo that has more of the apricot than the plum. Now, the other part of the weird joke of the conspiracy is that part of why I don't think these are all the same breed that we would call Pluots is that at the store that I go to right now, the produce store in my neighborhood, they have so many plum-like things that are all called Pluots. It's like this type of Pluot, that type of Pluot, that type of Pluot. I showed a green one the other day and a bright red one. And now I have 2 more colors of them. This one is also called a Pluot. There was, compare it, if you've seen the old streams, I showed like a bright green one, a bright red one. And look at this one. This one's like white-ish, like a very light yellow-green. Then, what about this one? This one I remember was called the Bubblegum Pluot. So, we'll take a bite. We'll see if it tastes like bubblegum somehow. It is like this very dark purple with these green specks. And it is pointy. Look how pointy this one is. Okay, sorry, graphs. We love you, graphs. Goodbye to the graphs for tonight. We're going to do Pluots and outro. Love you, graphs. You graphs do me so well. We'll come back to you in a few streams from now. So, these Pluots are radically different shapes and sizes and such. They had versions of these that were huge, but they cost too much. I don't have a huge budget. And genuinely, there was a type of these. These were $2 a pound, which I live in an expensive neighborhood anyway, so that's cheap for like what I could get a Pluot for in my neighborhood. And then there was ones that was $4 a pound that were like huge, so I didn't get those, but they come in like every shape and size. These ones are pointy and they're darker purple, and we're going to try the flavor of these real quick before we wrap up the stream. So I'll do a little taste test while you folks get to leave any last thoughts or comments, if anybody's around here and has any questions or whatever, before we wrap up. This one is tart and sort of like the green one I had before. Had a tart, sour apple-like flavor. But this one has like that mixed with a little bit of other Pluot flavor and a little subtlety, like almost the light yellowish green ones sometimes taste a little more like almost like a cucumber or a honeydew, that lighter flavor that some green things have. All right, now we're going to try the one that was called a bubblegum Pluot. Now look at the insides to see how different the colors are. So, that one, I will say it doesn't taste like bubblegum, but it's really good. It's delicious. So I don't know about if it matches the bubblegum title in any way or why it was named that, but this one is, if I had to pick one, I would have picked it because it has slightly denser flavor, a little more soul to it. Now, I'm going to eat the rest of those in a bit as I cook myself a nice steak dinner. Now, because I got a discount steak when I was buying these and stuff. Now, we'll do cooking tutorials sometime in the future. Now, I love you all. Thank you for watching. We'll do more graphs in a couple streams. I like to do these every couple streams mixed between. We'll do like, you know, a math lesson stream, me ranting about something I find fun stream, a game theory stream, and then a graph stream. So it'll come up every couple ones. And I hope you all stay tuned on the Combo Class channel. Like I said, I made some playlists of all of grade -1 in order and all the grade -2 so far. And the next episode will be the end of the first half of grade -1's main episodes. We're going to do the same amount of episodes as grade -1 had. So part of the reason I'm saying the next one is the end of the first half is at first, last grade had 36 episodes on the main channel, and I figured this grade maybe I'll do more, but I ended up deciding I'm going to do probably the same amount, but some will be longer. So there's going to be a higher ratio of longer ones, but there's going to be the same amount. And that's just for the main episodes on the Combo Class channel, and that means that if there's 36 again, this one's about to be the 18th. And that will land us at the halfway point. So not only make sure to check those playlists if you are bored some evening and want to just comb through a bunch of the grade. Also be tuned for in either tomorrow or the next day, either Tuesday or Wednesday, I'll be dropping that extra long, probably about half an hour episode about Point Infinite Nines that, despite it sounding like I've ranted about many of my thoughts about it this stream and last stream, trust me, there's a lot more in that half hour. So I love you all so much. I'll catch you again in more stuff. I will also be back to the shorts quite very soon, and other forms of content. Some of the things I've been working on that I can't share yet that take up some of my time include, I've shown you some of my beats, and I have been writing and finishing a lot of all the lyrics that are going to go on those on songs I'm creating. I have also been working on my novels, my fiction books that I hope to show you all before long. That won't conflict with Combo Class. It is all tied together in the Domotro dream. Now, thank you all for joining me. Hope you all have a great night or day, and I will see you again before